And so this is the blackbody spectrum here. This is the wavelength in microns, so 10 to the minus 6 meters. And so way out in the, at 3 microns, that's the infrared region. So we're measuring the light intensity as we get shorter and shorter wavelength, and you see it's going up and up and up, and then it turns around and comes back down. So this is the emission spectrum of a blackbody radiator. We talked about the Rayleigh-Jeans law and the UV catastrophe last time, and blackbody radiation and the Planck distribution. And this is a function of temperature. We see 3 different temperatures here. Now you experience this every day in your house and even in here in this room, okay? Notice how the lights against the wall are a little different color than the lights straight above you. Look here. If you go to the store and you buy light bulbs, they talk about color temperature, a certain Kelvin. And you have here on the left 27 Kelvin, 2700 Kelvin, which is, or here's 1000 Kelvin, very red light. And then way up here at 10,000 Kelvin, a blue light, and right in the middle are a pretty white light. So here's 5,000 Kelvin. It's white with a tinge of yellow. And look at our blackbody radiation curve here. Notice how we have all of the wavelengths, but it's a maximum in the yellow, and we have a little bit more red than we have blue. And so when you see these color temperatures on your light bulbs, they're telling you the blackbody curve that it's trying to match. Isn't that cool? So you've been dealing with blackbody radiation and you didn't really know it. It's the radiation that comes off of hot objects. And so if you have a light bulb with a hot tungsten filament, it gives off the light associated with these different temperatures. Now, how do we get the really high temperature light? We have to pressurize that filament with like a halogen gas, and that creates a much hotter filament and a much brighter white light. And that's where we end up with these halogen lamps being so hot. We've kind of gotten rid of them because they're fire hazards, especially the ceiling facing lamps. We would always have these Springer moths land on them, and then the moth would actually like char in the light, and it would stink, and it would make me like almost throw up. So my wife's like, stop, it's not that bad. But it was bad. So I'm glad we don't have those anymore. Now LEDs, they're trying to match these different color profiles. LEDs are light emitting diodes, and they give off individual like narrow spectral lines. And so they don't quite look right to your body. And so you'll notice somewhat different kinds of light from LED light bulbs. And it's because your brain, I guess, is expecting a blackbody curve, and it's not, right? And so something's not right. So even though you can't tell why, it just doesn't seem right. So this dashed line is the Planck distribution. But again, it's really difficult to think about this solid object with all of the atoms in that solid moving, and the equations for all of those electrons and all those particles are going to be too much for us. So I thought maybe I could model this blackbody curve with just a single electron on a wire. So just one electron on a tiny wire with quantized states. Now I've got to really crank up the temperature. Instead of 5,000 Kelvin, I have to go to 500,000 Kelvin because I've only got one electron. I might have like a quadrillion or maybe a mole of these little wires where all the different electrons have different energies. But I've got to heat them up to get an equilibrium distribution to give me that whole curve. Okay, so let's say I have a mole of electrons on a mole of little wires, and I have a temperature distribution of 500,000 Kelvin, and then I get this same kind of curve. So that's pretty cool. I have a few little humps down here, so it looks like I have 3 peaks here, but there's almost 50 peaks underneath this curve. And so what we're doing is we're simulating this blackbody curve with a particle in a box, that electron on a wire. And if you can simulate it, you have to know all the math that you put into the simulation. So that's what a lot of times P-chemists do. We'll go into it and say, well, if I can simulate it, I can understand it. And so we've simulated this blackbody curve with the particle in a box spectrum. And so now we'll take that particle in a box spectrum apart to look at the math underneath it.